calculation and all those things. That day I learned one thing, that if you want to be in IPR and do science as well as so-called administration in some way, the science part has to be done after 5:30 because the earlier part, you're busy, whatever, purchase, admin, this, that and everything. So that was a very learning thing for me on that day. And then I thought that why don't, because at that time no student joined me, I told let me start staying after 5:30, maybe it will help. And it actually helped. When people found that I'm staying after 5:30, some students joined, and then I was fortunate, I got the company of many good scientists in IPR and FCPT who helped the students to do their PhD. So in many sense, Professor Kaw was actually someone who, without telling anything, he actually gave us the directions that how to do science, how to do research and everything. And many of you probably benefited by directly getting associated, may have papers in conference or journals with him. So more on that about Professor Kaw, I'll actually call Professor Sen. Of course, we have worked together on some nonlinear systems, and we have a couple of papers also. And I have learned with all the people, like from Professor Kaw, Professor Sen, as well as Professor John, my PhD guide, my guru, and Professor Saxena. So all of us actually, they actually helped me, and maybe to many of you. So Professor Sen, you may please come. Please come.
Thank you, Subrata, and good afternoon to everybody. Am I audible? Oh, okay. Well, as you know, this is a very special day. Actually, a very sad day for all of us, IPR family. Because on this day, 8 years ago, we lost Professor Kaw. In a way, the father of this family, pater familias, or whatever you call him. But for many of us, he's still alive. He's alive in our individual memories, and I'm also sure alive in the collective memory of this place. As long as this family is active and remembers him, I think his legacy will never die. So I'm very grateful to Sudip and to Saroj for organizing this occasion, to reminisce about him, to think about memories, and actually derive inspiration from that again. Because as you all know, he was a very inspiring figure, and he has touched many lives amongst us, and each one of you must have a story to tell. I've had one of the longest associations with him. In fact, I met him first way back in 1971. It was in June 1970, June 1970 to be precise, at a meeting of a fusion energy conference of IAEA that was organized in Madison, Wisconsin. And my last meeting with him was towards the end of May in 1917, which I met in his office at IPR. It's a span of 46 years that I've had an association with him. This way, almost my entire professional life was spent in his association. Sorry? 27. Sorry, what did I say? 27 years. Typo there. It was a period of deep friendship and a very productive year in terms of research collaboration, and a time spent in partnership in institution building and chasing many dreams together. So as you can imagine, I have a rich reservoir of memories, and I cannot cover all of them here today. But my fondest memories are of the earlier years that we spent, years when both of us were very young and had big dreams to pursue. So let me share a few of those memories with you. Sudip is going to give a very technical talk on the work that he did with him and on the variety of topics that he had covered. I will touch more upon the personal aspect of his life and my fond association with him. So here's a picture of my first meeting with him. He had already joined PPPL, and when I went to this conference at the end of my graduate studies, I'm actually doing a postdoc at Oak Ridge. I went to this meeting. So just the evening before that meeting, it was kind of a small reception, and everybody was gathered around on the outskirts there. And I saw this young man. This is exactly what he looked like, standing exactly the way you see him here, with one leg resting on the wall. That was his characteristic style of standing. And he was arguing with the Pope of plasma physics, Marshall Rosenbluth. And they were engaged in a really vigorous conversation. And Marshall was there with his pipe, lighting it every few seconds, puffing away, and nodding his head. I asked somebody, who is this young man? And they said, this is Predhiman Kaw. I had heard of him, and his fame had already been there in the US. So after a while, after he had finished his conversation, I met him, introduced myself, and he immediately warmly received me. He told me that he was actually going to go to PRL very soon. And we had a wonderful time during those 4 days that we were at the conference. We did all kinds of activities. We went on a boat ride, rowing this boat in Lake Wisconsin. And I remember how it was so easy to go out into the lake because we had the wind behind us. Coming back was quite a struggle. So I asked him what was he arguing with Marshall so much. And he told me that Marshall had found an error in his calculation which he was going to present the next day. And that's what the argument was all about. Then he actually he stayed awake all night, went through all his calculations, redid them, and what he presented the next day was the correct thing to do. So that was the kind of person, and that was my first impression of him. My next meeting was, of course, in PRL, which he joined sometime in June 1971. And this was the era that I remember most fondly, because this was the golden era, according to me, of plasma physics and his life. So he joined in 71, and he had joined at the invitation of Dr. Sarabhai. What I was not aware of, Dr. Sarabhai, Vikram Sarabhai was the founder of PRL and space program in India, had actually gone around headhunting various parts of the world, including in the US. And he was one of the people that he had picked on to come and invited him to come and head a plasma physics and quote-unquote fusion program in India. Because Sarabhai had already dreamt of making a fusion program in India. It actually allocated some funds for it. Predhiman was privy to, but we didn't know. But he had originally gotten a group of about 7 people, senior people, to come and join PRL. I came back in October 71, and when I was there, I found that there was already this group in place, including Professor Bhuti, Professor Verma, Professor Pratap, Professor Sundaram, Professor A.C. Das. These were the people who were already there. And so this raised the first hopes of a fusion program in India. I say revival because originally there used to be a fusion program in Tata Institute, which was later disbanded because of some adverse results in UK. So we all started working very enthusiastically. Already in this 6 months' time, Predhiman had put together a very active program. So when Professor Sarabhai suddenly died in 1971, when we thought that this was the end of this program, it was not to be so, because Predhiman had already set things in motion, and he was still very gung-ho about pursuing this. So that is why the next few years were a very active period in plasma physics. We started a very intensive graduate program, training some of the best future plasma physicists. You might have heard of people like Parvez Gazatar and Sudip Sharma, who were all students at that time. Also developed a very vibrant theory group. We were all on the 4th floor, and that was our kingdom. And everybody envied us for that, because there was such an open atmosphere there. We'd be arguing and doing all kinds of things together. and people actually talked to each other. And one of the things that Predhiman did was actually to reach across to the experimentalist. It did not quite happen in PRL in those days. So he invited the experimentalists to talk with us. He took an interest in their experiments. And he also then started a small experimental program in PRL to simulate effects that one observes in the ionosphere. So this was Professor John had joined at that time, Professor Xana, Professor Mattu. And they started this experiment to study ionosphere, the electrojet actually, in the laboratory. So then also he had a very active research collaboration with many people within PRL and with the international groups, because he still had his connection with Princeton and with UCLA. And there was a great fellowship. This is the feeling that he really nurtured. As a young person, he was full of energy and full of dynamism. It took everybody by surprise there, and he actually created a very electric atmosphere. So he was the principal figure and a driving force in creating such an environment. If you look at him during those days, you can't make him out as a professor. He didn't look any different from any of the young people around him. These are all students with whom he was interacting, sitting out on the front lawn in PR. So that was the kind of personality he had. In fact, talking about research collaboration, that is when my first paper was published with him, way back in 1972. The way that happened was also very interesting. In PRL, we had a small faculty canteen on the ground floor, and you would have tea there in the afternoon. And sometimes you could just step out. There was a little patio kind of thing with casuarina forest, a lot of casuarina trees. And sometimes you would just go out there with a cup of tea and discuss things. That's when he first approached me there, and he said, "What are you working on?" I told him what I was. He said, "I have a nice problem. Would you like to join me in that?" And that's always how he did, how he got so many collaborations going. So he sketched this problem in a few lines, and we started working. That was a huge learning process, because the way he worked, the way he put the problem across to you, the way he made the whole process so transparent, telling you how he thought about it, how he analyzed it, and getting your feedback. So this was very quickly solved. In about a few months' time, we had already written a draft. And to finalize the draft, he said, "Well, let's meet somewhere else on a Sunday." On Sunday, we went to this little cafe. It's not there anymore, but you know where Law Garden is. There used to be a little cafe inside it called Busy Bee. So on a Sunday morning, we went there with our notes and everything, and we finished the paper right there. And that was his style of working. We would work on weekends, we would work at night, and any time was good time doing physics. So it was absolutely a constant learning experience for me. And particularly, this became very intense when we were traveling together. And I was very fortunate to have gone to many conferences with him and shared this unique experience. It was fascinating to see him engage in lively discussions with some of the very prominent plasma physicists of that time. And the respect that he got, even though he's such a young person, that really created a great sense of awe in me. The other thing was that he had this very innocent charm about him, which seemed to really win many hearts all around him. People just took to him very easily. Here's a picture of our trip to Hiroshima in 1974. We had gone to an IAEA conference, and after that we spent a month with Professor Nishikawa's group. I mention this because Sudip is going to talk about his collaboration with Mima-san. And you can see here Mima at the very end of this, standing right at there. Mima was a graduate student then with Nishikawa. And Hasegawa was visiting there. So it was a great group. And I think in that course of this thing, we even finished 3 papers with them.
At the same time, Hasegawa?
Yes, yes. We had a good time because we also would go on picnics, for example. And this is one picture where we went. You can see Predhiman carrying a big bottle of sake here. And the reason for this is that he loved Japanese food, but he did not drink. So they thought it was safe to give him that bottle to carry. talking about his innocent charm. He was childlike in many ways. I remember when we had gone to Japan, our kids were very small. They were toddlers, actually. So we had gone one day towards the end of our trip to buy some toys for them. And he bought a lot of them. When he came back to our room, he just couldn't wait. He started playing with some of them himself. Here you can see playing with this little doggy. He was also very athletic. He always wanted to explore the outdoors. Like whenever we went to a meeting or somewhere, he would go off. He could rent a bicycle and really go, hiking or running or things of that kind. Then he would come to the room and collapse. Take a nap for a few hours, and then he would get up and start working on his paper. One of the habits that I shared with him, they would always prepare our slides at the very last minute. So I was even worse than him, but then he was an early riser, whereas I was not. So whenever we shared a hotel room, he would get up at 4 in the morning. Rather than disturb me, he would sometimes go into the bathroom and write his transparencies there and then present them. And I said, why do you do this? And of course, I had the same habit. He said, unless you do that, your talk doesn't become very fresh. Prepare it a month ahead, it will become very stale. So that was his philosophy. Here's a trip to Moscow once, and you can see how he's shivering in the cold. We were not really prepared for that cold weather. You can see I have a raincoat. I had borrowed that cap from one of the Russian scientists there. And Predhiman, as you can see, is shivering up there. One of his peculiarities was that, he comes from the northernmost part of India, Kashmir. You would feel that those guys would not feel so cold. This winter in Ahmedabad, with the first sense of changing atmosphere here, he would be the first one to wear a sweater. Whereas people from the south, my friend Dr. Sundaram, whom many of you know, he never wore a sweater in Ahmedabad. But Predhiman was always the first one. He would come with his jacket, with his coat. Well, all these good times came to an end in 1975. Because by that time it was clear that there was no funding available from the government. So he was quite disappointed about that. And therefore, he decided to go back to Princeton, where he had an offer again. It was a sad day for many of us. I remember when he came to my office, we were finishing a paper. We finished that discussion. At the end of it, he announced that he was going back to Princeton. But he said, you take care of the student. Parvez was registered under me. And then he said that, I hope we'll meet again soon. We'll carry on from there. And sure enough, we met very soon, because a year later I went on a sabbatical to MIT, and we got in touch again. Those times were very exciting in the US for tokamak research, because both at MIT and other places, they were getting very exciting results in tokamaks. We felt that this was the right time. If you wanted to do fusion research, this was the right time to launch a program again. So we got together and started planning for that. So whenever we went to a meeting, either APS or Sherwood meeting, all the people, all the Indian delegates would get together in some hotel room, and we would discuss how to go about it. And that's how these things started. So when I came back, talked to all the people here in PRL, Professor John, Professor Saksena, Mattu, and all that, and they were also excited. So we started already planning for a fusion program. But in the meanwhile, I had to chase all these government agencies to try to find some funding. It was a long and very labyrinthine chase through all the various departments. But finally, I think we were able to convince them, and the file landed on Professor M.G.K. Menon's desk. Predhiman, of course, kept track of this from in Princeton. So when I called him and said that looks like we might make a headway, Professor Menon has asked for a meeting, can you come? And immediately he came. And we had this meeting with Professor Menon, who was then the secretary of DST, in his office. That was in a way a turning point, and I remember that meeting very well and very vividly. Because Professor Menon, as usual, had files all around, and we could see him just through them. But he sat us down and we discussed it. He had, of course, read everything. He summarized everything very nicely for us. And then he made a proposal. He said that, yeah, we can have a program, but it has to be more general than what you want. Predhiman was, of course, very intent on a fusion program. He kept pressing him on, no, but we want this. This is the status of the fusion program in the world and all that. Menon kept nodding his head, and I could see that he was inclining more and more back in his chair. So, but fortunately at that time his phone rang, and he had to go out somewhere. Somebody said, he said, okay, I'll see you another 15 minutes. That was a lucky break, because when we came out of his office, I said, look, he's giving us an opening. Let us take it. And all he's saying is that you should have links with universities. You should also have a basic program, not just fusion. He immediately agreed. And when we went back, he said, fine, it's fine with us. That was, and Menon, of course, agreed. And that's how the first program in fusion got started. It was nucleated in PRL. It's called the Plasma Physics Program. And that's how, that was the beginning and basic root of this place. So here's the chronology. I'll not go through the whole thing. Most of you know. 82, PPP, or the Plasma Physics Program, was established in PRL. 86, IPR was established, still under DST. The first tokamak Aditya was commissioned in 1989. And then, of course, you know, SST-1 came in 1994, and we became part of DAE. Each one of this has a long story associated with it, which is always very fascinating. For example, the way he got SST-1, I don't know if you know it, but at that time, there was a small newspaper item, forget it was the Indian Express or Times of India, it said that China has embarked on a superconducting tokamak. A junior level officer in DST took that clip and sent it to the PMO. PMO sent a query to the atomic energy. What are we doing about this? And the PMO actually called a meeting. So messages went out to RRCAT, to IPR here and all that. But the thing is that Predhiman was ready. In 2 days, he gathered everybody, collected all material, and actually prepared a proposal. Everybody else was caught, but nobody took that seriously. People otherwise said, oh, we want a little extension to our program and this and that. He was bold enough to tell the Prime Minister that this is what we want, this is what we need to do. And he got approval. That is how SST-1 was established here in IPR.
That was still under DST.
Yeah, but then very soon after that, we moved to 1996. We moved to DAE because because the program was growing very big, and DST could not afford to support us at that level anymore. And also, this nuclear aspect came in when you talk about fusion so much. So, if you look back now, you can see from a simple low density, low temperature tabletop device that he had devised in PRL, making India a full partner in ITER, all in the span of a single lifetime, an amazing achievement, which speaks, volumes about his vision, his leadership, his scientific and technical ability, and his total commitment to this cause. He devoted his entire life to this. So, truly, he was the father of the Indian fusion program. Let me spend a few minutes on his persona. Because despite all these achievements and all the awards that he got, some of you have seen that in the library, and the high offices that he had occupied, he remained as simple and down to earth as I had first known him. He was marked by a tremendous passion for science and an immense curiosity. This can be seen from the wide variety of things that he worked on. He was marked by a tremendous passion for science and an immense curiosity. This can be seen from the wide variety of things that he worked on. His forte, he started his life working on nonlinear processes in plasmas, parametric instabilities and things of that kind. But then he branched out into so many different areas of plasma physics. Whether it's tokamak or the turbulent phenomena or dusty plasmas and hot gluon plasmas, what Sudip worked on for his thesis. It was amazing because he had this capacity of making connections between different parts of physics across different disciplines. And he could translate an idea from one discipline to another. And dusty plasmas is one classic example. He was working on quark-gluon plasmas, where the charge itself is not a constant quantity. We thought that would be a good idea to translate to dusty plasma, because dusty plasma is dust, it requires charge, which is time variant because it. And that's how he could translate immediately from one field to another. And he gave this talk at an international conference, and people were fascinated. After that, many papers started coming out on the charging of a dust particle and how it is time dependent. But above all, I think what he was mostly devoted to was to his colleagues and to his fellow workers, and how to transfer his knowledge to them, to train them and spend time with them. His working style was also very unique. He had a strong belief in academic freedom and a work environment conducive to creative work. If you look around, the way this institute is designed, the way this whole place was set up, the structure of this place, you can see a reflection of this. That he really wanted ideas to flow freely, no hierarchy. As Mukherjee said, his door was always open, you could go anytime. And despite all this administrative work, he always had time for physics and for science. So his belief was minimal administration that facilitates and supports scientific research. He also had an idea that this institute should be free and open to all, not just nationally, but even internationally. So during his period, this place used to be flooded with visitors from abroad. And we had some of the most exciting speakers and talks at this place. So what was his legacy and what was his dream? I think his legacy is well known, and you can see it all around you. He created this world-class research institute and gave it a unique work culture. He also inspired and trained a large number of young scientists in the field, who are today he's spreading his knowledge all over the world. One of the examples is Sudip right here. That's what he's doing. He's going to talk about the work that he did with Predhiman. Also, he was responsible, almost single-handedly, in getting India into the World Fusion Program at a very early stage, and also actually drawing a roadmap for its future growth. Fusion, as you know, has had a very checkered history. It has so many promises and it has failed so many times. So there were many skeptics, people who didn't actually believe in fusion. But he was one person who ardently believed in fusion. And he thought, even with all the things that were happening around and all the skeptics around, he believed in the success of fusion, and he believed that India will be part of that success. It's a pity that he's not alive today, because in the last few years, it's a sudden upsurge of interest and support for fusion. I would have been delighted by that. But this is what his predictions are coming true. And he would have taken maximum advantage of that and pushed us into a different direction. But the way that it is, I think on this day, all of us here in the IPR family remember him and who know his legacy. I think it is our duty to preserve that legacy and actually take it forward and do our best to fulfill his dream. That is the least we can do. And I hope some of us will do that and continue to do this. Thank you very much. Okay, 2 minutes extra. I think 3:30.
He's taking it?
3:30 take a check.
Okay, dear colleagues, I'll read from my diary few lines, okay? So, we have assembled here to commemorate the 8th death anniversary of Prof Kaw. To honor his legacy, I am going to present some of my work which I did with him. Okay, and also I'll acknowledge the passing of Professor Mima, who was a close collaborator of Prof Kaw on this year on 5th January 2025. So my talk is divided into two parts. Okay, so first part I'll talk about relativistically intense waves, but longitudinal waves, the work which I did with Prof Kaw. And then I'll talk about, in the part 2, I'll talk about transverse relativistic waves, which was inspired by Professor Mima's work. And I had some discussion with Mima. So I was initially planning to give a popular talk, okay, but then I realized that preparing a popular talk is very, very difficult. So, in fact, I remember what Professor Kaw once told me, that if you want to become unpopular, try to give a popular talk. So what I will do is, I'll show equations, but I'll try to give analogies and, wave my hands and try make it as accessible as possible. Okay? Right. So we begin. So by part 1 of the talk. Okay, so we'll start by asking a very simple question. What is a relativistically intense wave? Okay, that's the first question, right? From the title. So a plasma wave is said to be relativistically intense when the electrons, while oscillating, achieve speeds close to the speed of light. So basically, the energy which is gained by an oscillating electron over a distance of one wavelength becomes comparable to its rest mass energy. So such gigantic waves are nowadays routinely encountered in many areas of plasma physics. One of the examples is that if you shoot a laser pulse, intense laser pulse through a ionized plasma, ionized gas, in the wake you will see intense waves which are relativistically intense. So that's one example. Another example is you shoot a electron beam through a plasma. Again, in its wake, you will see, if the beam is intense enough, you will see relativistically intense waves. So this is one cartoon. This slide is very old. I was planning to actually make a PPT out of it, but then I thought the vintage character should be kept. Okay, so it's like this, that you imagine a laser pulse. Okay, on left hand side, I think this moves. Okay, so this laser pulse is moving through a plasma. As it moves, the radiation pressure from the pulse pushes the electrons to one side. Okay, but the ions which are left behind, they pull the electrons back. So push by the laser pulse, the pull by the ions. Push by the laser pulse, pull by the ions, excites a plasma wave in the wake, which is what you see. So you have a push by the laser pulse and the pull by the wave. Okay, so a laser pulse, if it is intense enough, these oscillations can become relativistic. So while the electrons are oscillating about the ions, these speeds can become close to the speed of light. Okay, right. Another example is that if you shoot a electron beam, again the electrons in the beam will repel the plasma electrons. Mukherjee. Okay. So electrons in the beam will repel the plasma electrons, and the ions will pull the electrons back. So again, a push-pull mechanism excites the wave at the back. You can sit down, Ganesh. Okay. So this work, so what I am going to do is, so these are relativistic waves. What I am going to do is, I am going to slowly trace the history of this work, the work which started in IPR. So this work basically started from one work which was done by Kaw, Sen and Kotsoulis in 92. So what they did was they took the relativistic fluid equations along with Maxwell's equations and wrote down a solution which is like a light wave trapped inside a plasma wave. So how do I understand this solution without looking at the mathematics? So see, suppose if you want to communicate with a satellite, okay, so you send a wave, its frequency should be more than the plasma frequency of the ionosphere. Now, if it is less than the plasma frequency of the ionosphere, it reflects from the ionosphere. Now, what this solution is, that this is a light wave. As it propagates through the plasma, it digs a hole. And on both sides, the plasma density becomes so large that the light wave reflects to the front and reflects to the back and gets trapped in the hole. The whole thing then propagates as nonlinear intensity inside the plasma. Okay? So I have a light wave which is oscillating here, which is trapped inside a plasma wave. So this solution was written down by Kaw and Kaw in 92. So one of potential, scalar potential and vector potential. Okay? Yes, in the moving frame. So Vikrant, one of our student, was simulating this with Professor Sen. Okay? What they found that under certain conditions, as this entity, this nonlinear entity moves to the plasma, it excites certain spikes in its wake. So one day, Professor Kaw called me. He said, do you see these spikes? Let's try to explain them. Okay? So his idea was very simple. He said, okay, as this thing moves, this is like a boat moving through a plasma sea. So at the back, it is exciting wake fields. So what he said, that let's take a simple problem. Take two waves whose wave numbers are separated by delta k. Okay? Take these as initial conditions, feed them into the relativistic equations, and work out the consequences. Statement is very simple. Okay? But when we tried, so to solve this problem, first of all, we looked at the most basic paper on relativistic plasma waves, which was by Ekhath and Polovin. This is another picture of that. 1956. Okay. So what they did, they started with, okay, Mukherjee is very happy. Okay, so they started with the fluid equations and the Maxwell's equation together and wrote down propagating solutions. The idea was to take those equations, solve them, and use these as initial conditions. So initial condition will be two waves whose wave numbers are separated by delta k. Okay? Now this is a very difficult problem. So what we did is we changed the model. Okay? So we took a model which looks something like this. So we went back to FF10. Okay? So now you take a one-dimensional model where the electrons are assumed to be sheets. This model everybody has seen, every first year student has seen. Okay, so you have electron sheets which are the equilibrium position. So as you displace the sheets, they come back to the equilibrium position and start oscillating. Okay, so this is the 1D model. Okay, so assume that the electrons are infinite sheets of charges which are embedded in a cold mobile positive ion background. So xi is the displacement. As you can see that if I count the number of sheets per unit length, that immediately gives me the density. Okay? So with this model, we thought we'll first excite the wave by displacing the electron sheets, okay, and then study its evolution. So that was the purpose. Now this model, this is not just a simple cartoon. This model has a mathematical justification. The justification is the following. Don't worry about these equations, I'll explain. Okay? On the left hand side, all of you have seen these equations. Left hand side is continuity equation, the force equation which is Newton's law, the third is Poisson's equation. Now if you feed it through a transformation, which is called a Lagrange transformation, you immediately see that the density equation of motion and electric field becomes exactly same as what is given by the Dawson sheet model. Okay, so this model, this simple model represents these equations geometrically. So what we did is we thought, okay, we'll take this sheet model, write an equation of motion for each electron, okay, and write out a solution, and then give the density and velocity as an initial condition. Okay, that was the problem which we tried. You can stop me in between if you have questions. Okay, right. So this is a figure of a one sheet which has displaced from its equilibrium position. If you calculate the force at this point using Gauss's law, you can immediately write down the equation of motion, which looks like a nonlinear oscillator equation. So what Professor Kaw said, we will use this equation, use the initial density and velocity as wave-like solution and feed and okay. So what we did is we took this equation initially. Initially we didn't know how to solve this because this equation is non-linear. So although an exact solution exists, but at that time we were not aware of that. So what we did was we linearized this equation in the weakly relativistic limit. So as you can see on the top, if you remove this part, it looks like a simple oscillator, x double dot plus omega square x equal to 0. And that this portion is a nonlinear term which changes the frequency of the oscillator. So this was solved using a method which is given by Bogolubov. Okay. So what you do, the method is very simple. You say x is amplitude times sine of omega t plus phi, substitute in this equation of motion and do some averaging, and you will see that the solution has a frequency which is nonlinear shifted, and the nonlinear shift depends on the position of the sheet. So which means that each electron is oscillating with a frequency which depends on its position. Okay. Now let's look at the cartoon now, what I said. Okay. Forget about these equations. Okay. Let's look at this picture. The top one represents simple plasma oscillations. Okay. So you have displaced each electron from its equilibrium position, leave it, and they oscillate with the plasma frequency. Here each electron is oscillating with the same frequency. Now look at the second figure when the plasma frequency becomes a function of position. Look at this equation. See here the frequency of oscillation is a function of position of the sheet. So now look what happens. So suppose each electron starts moving with a frequency which depends on its position. So what will happen that very soon you will see electrons coming and sitting on top of each other. You will have a phenomena which you see on the seashore. Basically, you have waves. As the peak rises, it overturns. So this is a phenomena which is called wave breaking. Let's go back here again. So in the second case, you can see the electrons piling up at certain location. Exactly the similar thing which will happen in a seashore. So the wave goes, you can see at one particular location, you have two velocities, one velocity going in the left, one velocity going to the right. Exactly the same thing which you see here in these pictures. Okay. So this phenomena is called wave breaking. So this is what we suspected is happening in the simulation which Professor Kaw and Professor Sen and his student were doing. With this scheme, we took the initial density and the velocity and fed to the solution. Okay. Now forget about the math again. So these are the initial conditions. If you look at these initial conditions, if you choose wave number difference to be equal to 0, it looks like a propagating sinusoidal wave. And if the delta k is minus 2k, it means like a simple oscillation. So you have two waves which are propagating towards each other, and that looks like an oscillating wave. Okay, so there are two cases, a propagating sine wave or a oscillation. So using these initial conditions, we can calculate the amplitude and, I'll go back, amplitude and phase of this oscillator, this solution. Okay. It turns out that if you have a single wave, when delta k is 0, the frequency becomes independent of position. So you have a simple sinusoidal wave propagate through an electron ion plasma without breaking. Okay. But if you have an oscillation, then the frequency again you see depends upon the position of the sheet, and this results in a phenomena which is called breaking. So this is what happens. Pictorially it is this. The second case. So first case is when delta k is 0, and the second case is when delta k is minus 2k. Okay. Is the problem clear? Okay. So finally, when we wrote down the density, it shows an expression that the denominator has a term which depends on time. A time comes when the denominator goes to 0 and the density shows a burst. Exactly the thing which was seen in Professor Sen's simulation. Okay, so this is one of the picture which is from the simulation. As you can see that you have, as the simulation starts, as the nonlinear intensity propagates, you will see waves at the back, and those waves after a certain time show the burst. And this burst was calculated for recurrence simulation, and our theory shows a very good match with the simulation result. So these spikes, which I showed in the beginning, is happening because of a phenomena called phase mixing. So electrons at the rear of the pulse is actually oscillating with a frequency which depends on its local position. Frequencies are different, so as they oscillate, they come and sit on top of each other, and you see a density burst. Okay, this is the basic phenomena. Okay, so while I was doing this calculation, one day I showed this figure to Prof Kaw. Okay, so since this calculation is a perturbative calculation, it was not an exact calculation. So what happened was my points, these points which you see, which is from the simulation, were actually lying like this. Okay. Yes. So this is the theory, and the simulation points are lying somewhere here. Okay. I thought it's okay because since the theory is approximate, the simulation may not match the theory. I don't exactly remember what argument Prof Kaw gave. He just looked at it, did something on a piece of paper, and said it's wrong. He just said that you have made an algebraic mistake somewhere. I don't know, I don't exactly remember the argument here, but then I went back and checked, then I found that actually the simulation points fit the theory much better. Okay, so there was the algebraic error in the calculation. Now the situation is, if you see that you have a relativistic wave which breaks, okay, because of a phenomena which is called phase mixing, that at each spatial location the oscillating electrons are oscillating with a frequency which is position dependent, and hence the wave breaks. Now going back to Akhazer-Polovin's paper again, okay, here is one paper which showed that there exists a solution which does not break. So what is our calculation? Okay, so what we did, we said, okay, let's try to solve the problem exactly now, and eventually we found an exact solution of the problem. I will not go through the exact solution, but I will show you a picture of this movie. Movie is not running here. Okay. So this was the solution. This is a propagating wave which propagates in a relativistic plasma without breaking. Okay. Whereas our theory which we did, we showed that all relativistic waves should break because the frequency of the oscillating electrons depends on the position, and hence while they are oscillating, eventually these electrons will come and sit on top of each other, and you will have a density burst. But here we have a solution which doesn't break. So what we thought, okay, we'll look the solution to this problem must lie in the exact solution of this equation. Okay. I will not go through the steps. Okay, simply tell you what it is. Okay, you have an oscillator. Okay, the first step can be easily done by any first-year student. You multiply it by a velocity, and you can write down an energy equation, which is the second term equation. Okay, so you can see that this is again a first-order differential equation, can be solved, and it was solved by one of our student who was working with Prof Kaw and myself, and he showed that you can write down an exact solution for the displacement. This equation showed that depending upon the choice of initial conditions, your frequency can either depend upon the initial conditions or could be independent of initial conditions. Okay, so you have, okay, let me go back. So this is an oscillator equation. I is oscillating, okay, with certain frequency. Now depending upon the initial conditions, the oscillator may show mixing or may not show mixing. Okay, so this is the final result. We showed that the oscillation frequency depends on the initial choice of initial conditions. So if you choose any arbitrary condition, like the condition which we were doing, or the condition which was generated by Professor Sen's simulation. For any arbitrary initial condition, the frequency can, in general, become a function of position and the wave can die. Okay? But you can choose a very special set of initial conditions for which the frequency is independent of position and the oscillations do not die. This was the Akhazer-Polovin's work. So we studied this in depth, and we found the Akhazer-Polovin solution is a very special solution which requires very special initial conditions to be excited. In general, any relativistic wave will always die, but just because of relativistic effects. So that was the conclusion of this work. I'll skip the simulation part now. So this was our final result, which I remember when I was doing this work, Prof Kaw once called me. He said, well, we were discussing, we said Akhazer-Polovin mode, the work which was done in 56, is actually a solution which is of zero measure. Actually, it should die. He jokingly said, Akhazer-Polovin ko gali mat do. That's what he told me. So now, it was a joke. He said, Akhazer-Polovin ko gali mat do. 1956 ka kaam hai, so it must be okay, good. But then later, when this paper was accepted, he called me very early in the morning. He used to get up, I think, at 3 o'clock. So he called me at 6 o'clock. He said, Sudip, paper is accepted. So that was the time. So, okay. So now I go to the part 2 of the talk. And okay, this is one of the application of our work. So if you have an electron beam, or a laser pulse going through a plasma, which is cold, the plasma has no choice but to excite a Akhazer-Polovin mode. So that you can see that this is a simulation. You have an electron beam propagating through the plasma. At the wake, it is exciting Akhazer-Polovin mode, and theory and simulation are matching very well. But very soon you will see that the theory starts deviating from the simulation, and these bursts are coming because of a phenomena which is called phase mixing, which is the content of this paper. Okay, so next part is slightly more heavy. Okay, this was a simple part because we are talking about only longitudinal waves. Okay, so next part was done with transverse waves. Okay, so here I will, before I go into the main part of the talk, I will first tell you how this work started. So we were attending a conference in 2019. It was just before COVID. I think 18th November 2019, COVID was found in China. So we were there, I think, up from 6th to 11th November. Okay. So this was an idea which was floated by Mima. He said that if you shine light on a plasma, there is a mechanism through which you can directly transfer electromagnetic energy to the ions. Generally, what happens that when you put laser light onto an ionized medium, it is the electrons which take up the energy, and then from the electrons, the energy goes into the ions, which is a very slow process. Whereas here is a scheme where there is a direct transfer of electromagnetic energy to the ions. The scheme is very simple. What you do, you take a Whistler wave. Okay, Whistler wave is a right circularly polarized light moving along the magnetic field, having a frequency which is lower than the electron cyclotron frequency. Okay, so you have a Whistler wave propagating, and you take another Whistler wave which is coming from the opposite direction. So as these Whistler waves interact, they produce an electrostatic field. Okay, this electrostatic field, ions get trapped in the electrostatic field and accelerate, and thus soak up energy from the electromagnetic wave. So this is the scheme which was proposed by Mima's group. So when they were presenting this paper in AAPP DPP conference, so I immediately asked Professor Mima that what they had done was the simulation was relativistic, whereas their calculation was non-relativistic. So I knew about Akhazer-Polovin's paper. Okay, so Akhazer-Polovin had written a relativistic version of Whistler board. So which means that you can do an exact relativistic calculation and try to match with the simulation. So So when I told this to Professor Mima, he just looked at me. He said, yes, you can do it, but you cannot do the finite temperature part, which is of course. Finite temperature part is more difficult. Okay, so here is a brief tutorial on what is a Whistler wave. So Whistler wave is a right circularly polarized electromagnetic wave with omega smaller than omega CE. One property of the Whistler wave that it has no cutoff. Okay, it can straight away drill through a overdense plasma. You look at the Whistler wave dispersal relation, when omega is smaller than omega C, this becomes positive. So any value of K will work. Okay? Right. Now, third thing is it does not couple to any longitudinal fluctuations. So it just a circularly polarized light which simply goes to the plasma. Now, if you look at the relativistic dispersion relation, you will see that the equation looks seductively similar to the non-relativistic version with just Lorentz factor thrown in at the right places. So plasma frequency gets replaced by the relativistically correct plasma frequency, and the cyclotron frequency gets replaced by the relativistically correct cyclotron frequency. So this was our clue. We said if the math can be done with this, it can be done with this also. Okay, so I give you a brief. Okay, here is Professor Bhima with Amit, who was also in the conference, and I'll talk about Amit later. In fact, Amit designed an experiment to study what we did. Okay, so I was also in this conference, but I'm not in this picture. Okay, so I don't know where I was, but I was somewhere behind maybe. Okay, right. So Mukherjee, we go back to Akhezer-Polovin again. Okay, but this time we look at the transverse part of Akhezer-Polovin wave. Okay, so this is why do we do it? Because this is one of the first work on relativistic plasma waves, which was done by them, and where wave-like solutions of the Maxwell-Lorentz set was derived. So relativistically intense Whistler waves is basically a transverse Akhezer-Polovin mode. Okay, so excitation is common nowadays because of intense lasers. Okay, so I give a very quick derivation of this because this part is very simple. All of you will understand. Okay, the first part is simple Maxwell's equations which are relativistically correct. Okay, and the second part is the Lorentz force equation, which is where you take the relativistically correct equation. What you do is you play with them. Okay, and write 3 differential equations where for momentum. In fact, these are actually 4 partial differential equations, 4 or 5 partial differential equations. You look for solutions which are propagating and then convert this into 3 differential equations, for 1 for longitudinal motion and 2 for transverse motions. Okay, where Z is the direction of propagation. So we now look for solutions. So if you look at these equations, you can write density in terms of velocity, magnetic field in terms of velocity, electric field in terms of velocity, and all you need is an equation for velocity. Okay, so you have density, magnetic field, and electric field in terms of velocity, and 3 equations for velocity. So now what do? We said we want an equation for which the Z component of velocity should be 0. Okay, so you look at the Z component equation and put uz equal to 0. Now, if you put uz equal to 0, this equation admits a very simple solution, rho square equal to constant. You see, this is 0, and rho square equal to constant. So once you, okay, so since rho square equal to constant, you choose a solution which is like a circularly polarized. I will not go through these equations again, but I will show you, I will take your attention to this one first. Okay, so you have a circularly polarized light, okay, propagating through the plasma. It does not excite any longitudinal motion. Okay, you have another circularly polarized light coming from the opposite direction, which does not excite any longitudinal motion, right? But these 2 waves together, the magnetic field of this wave coupled with the velocity of that wave, and the magnetic field of this wave coupled with the velocity of this gives rise to a longitudinal motion. So that comes from the conservation of longitudinal momentum. Whistler waves do not carry any longitudinal momentum. So if you combine two Whistler waves, the longitudinal momentum should be conserved. So from that conservation of momentum, you can calculate the Z component of electric field. So this was what we did. Okay. So now, in order to calculate the electric field inside, you match with the electric field which is coming from the laser. Okay. So that is given by the Fresnel equations. So this was, in fact, this is one of the idea which was proposed by Mima's group. So you calculate the electric field inside, and okay. The calculation which was done by Mima's group is given in the lower portion. They did the non-relativistic case and they calculate the electric field, the Z component of electric field, exactly in terms of the parameters of the system. Whereas when we did the relativistic calculation, we landed up with this complicated equation which we had to solve numerically. So now I show a picture of what we did. So you have a circularly polarized light propagating in. The light is, part of the light is transmitted and part is reflected. So you can calculate the amplitude of the reflected and the transmitted light using Fresnel equations, and it turned out that our solution of this equation matched the simulation very well. So here is another simulation. You have one light wave propagating, this is just one circularly polarized light propagating. This is simulation from using Osiris. So I do it again. The red color here is the transverse field. So as I had stated before, the Whistler wave does not produce any longitudinal field. Longitudinal field is represented by blue color. So you can see it's hardly producing any longitudinal field. Now we took two Whistler waves. Okay, this is just shows that our simulation results matches the theory very well. Now you take two Whistler waves and look at the simulation again. Sorry. They superimpose and produce electrostatic field which is given by blue color. Okay, here is a magnified picture of the same thing. We theoretically calculated this blue electric field, which is a longitudinal electric field, and see how good the simulation is. So here is the final simulation result. So as the waves are coming together, they produce a electrostatic field in the center. So when the electrostatic field peaks, you take a snapshot and plot the non-relativistic and relativistic results together. You can see the non-relativistic result does not match the simulation very well, whereas the relativistic results matches quite well. Okay. So this is a vindication of the relativistic theory. So when I showed this to Mima, I wrote him a mail. So this was around 2021 when the COVID was very strong. So I said that we have done some work and improved your calculation using in the relativistic regime. So can you please comment? And immediately, next day, I got a mail which says, Sudip, the calculation, although relativistic, the results are not relativistic. The reason was the following. He said that in your simulation, you have chosen so strong magnetic field that the electron, while moving, the magnetic field is not allowing it to go to relativistic speeds. So it is circling around the magnetic field, but not reaching relativistic speeds. So when I checked, I actually found that this is true. So although the calculations are relativistic, the reason that the electric field is weak is not because of relativistic effects, but because of strong magnetic field. So let's look at the electric field again. You see that the electric field is weak compared to the non-relativistic case, but it is weak not because of relativistic effect, but because of strong magnetic fields. So this was one thing which, when I saw this mail, I took probably several weeks to understand what Professor Bhima is suggesting. So after that, I realized that thing was wrong, but before I could make changes, the paper got accepted. So this is one time where actually was unhappy that the paper got accepted. Okay, so this particular work was used by TIFR people, and they designed an experiment. They said, okay, with this scheme that you taking two counter-propagating Whistler waves, you can design a tabletop thermonuclear fusion experiment. Okay, so idea was proposed, and it was proposed. It was put to Infosys TIFR leading edge grant. In fact, there were 10 projects which were submitted for this, and out of this, only 3 were selected, and this was one of them. Okay, so I'll tell you what the project is, or what the scheme, what the experiment is. So let me try to explain the experiment here. Okay, so you have a laser light coming from the left, which is the TIFR 800 nanometer 3 joule laser, and at this point, the light gets deflected into two parts, and the part which is coming here reflects from this mirror and falls on a target. This target has 3 portions. One which is a DD target having deuterium in it, and there is an aluminum foil on the side. Okay, so what is happening when this light is circularly polarized? Okay, so when the circularly polarized light falls on this target, it blows up this target and produces circular electron currents, which produces a very intense longitudinal magnetic field. Okay, and this magnet, although this laser is of 27 femtosecond, the magnetic field which is generated is of picosecond time scale. So as the magnetic field peaks, the other part of the laser light is then converted into two circularly polarized Whistler modes, and they fall from 2 sides. As you can see here, so this is one beam, and this is another beam, and they are falling on this target. So they excite electrostatic fields in this target, and it is expected that in this electrostatic field, ions will get accelerated and fuse and produce neutrons. Okay, calculation was done, and what was found that this scheme can produce 10 to the 9 neutrons per steradian per joule. Okay, so this experiment was approved by, supported by Infosys TIFR grant, and some initial experiments have been done. This is in progress, but when I spoke to Amit yesterday, he said that the TIFR laser is now around more than a decade old. So when they try to jack up the intensity, one of the optical components go bad. So it is taking time. So, but I think that once this is done, this will give rise to a very neat neutron source. There's one more interesting thing about this target, that this target, they are going to put E. coli bacteria in this target. The reason for this is that E. coli bacteria has ellipsoidal shape. So if the target is corrugated with E. coli bacteria, the laser light interacts with this corrugated surface and produces surface plasmons and results in intense absorption of the light wave. So this is something which is their idea, and that's why in this team there are 2 biologists also. Okay, I still have 15 minutes left. I think I'll conclude here. So conclusion is, of the first part, is that relativistically intense longitudinal waves break because of relativistic effects. Okay, and the breaking time goes as 1 upon the amplitude cube. And this result is independent of geometry. We have done this work for cylindrical waves, for spherical waves, with magnetic field. This is all the time goes as 1 upon amplitude cube. Second thing is, relativistically intense transverse waves, which are Whistler waves, they offer a new scheme of achieving thermonuclear fusion, which is a tabletop neutron source. Experimental demonstration has been proposed, has already been proposed. One final thing is that if you really want to do theory for this experiment, the second one, you have to do a kinetic Akazer-Pole wave. Mukherjee, which is for next another decade, will be the work for the future generation. And you won't believe me, when I was talking to Professor Mima about this problem. He immediately said that you need to do a finite temperature calculation. Okay, and finite temperature calculation is not easy. A relativistic fluid with finite temperature is a different ball game. About 10 years back, when I was doing Abhijit work with Professor Kaw, he had exactly told me, Sudip, Abhijit ko gali mat do, maybe you should try to do a finite temperature calculation, which is, is a more difficult calculation. So both of them said that the future is finite temperature Abhijit. Finally, I list all the collaborators here. Predhiman Kaw, the work which was suggested by Professor Kaw, Amita here, Amita is somewhere here, Professor Sen. In fact, as you remember, the work actually started with Professor Sen's simulation. Okay, so, Vikrant was Professor Sen's student, as right now in IIT Delhi, and Orgo and Ratan. Orgo did the spherical calculation and also the cylindrical calculation. And again, in all cases, we showed that the relativistic waves break because of relativistic effects, and the breaking time goes as 1 upon delta Q. Ratan did the simulation with the electron beam. So these pictures are from Ratan's simulation. These pictures, Ratan did this simulation with a fluid code. So he took an electron beam and passed it through a cold plasma and found that it excites relativistic waves in its wake. Okay, so now other people here, Nidhi did the work on magnetized relativistic waves. Okay, her thesis was on that. Acha, Mithun and Bhavesh Patel. Bhavesh Patel is not here. Bhavesh Patel is very invisible. But Mithun and Bhavesh Patel did the work on relativistic Whistler waves. And with Arvinder, we did some work on wave breaking, but in the non-relativistic regime. Finally, Ravi and Amit were involved in designing the experiments. Thank you. I finished in 45 minutes. If you want, you can ask questions. Huh.
Ultra-fast interaction of wave particle that you showed.
Huh.
Can one say that two counter-propagating waves, Whistler waves, are forming a stunning wave, and it is interacting with plasma? Can you say it's a special case of inverse Landau damping?
No, it is not inverse Landau damping. So this is all cold plasmas. Okay, so these are. So the electric field is coming because the plasma is trying to conserve longitudinal momentum. Okay, so a single Whistler wave carries 0 longitudinal momentum. The second Whistler wave carries 0 longitudinal momentum. Both together, since the longitudinal momentum has to be conserved, it generates a longitudinal electric field. So the force on the electron goes to 0. Okay.
So the energy comes from where? The plasma or the waves?
From the waves. From the waves. Yes. From the waves. Yes.
It dies down.
Yes. From the electromagnetic wave.
The Whistler wave.
Whistler wave. Yes. You have to use energy to generate Whistler waves, and then Whistler waves transfer energy to the plasma.
Is there any threshold of energy in Whistler waves, or it can?
Yes, you need magnetic fields of the order of 10 kilotesla. Okay. Now, yes, 10 kilotesla magnetic field can be generated. It has been generated in intense laser plasma interaction experiments. We have a paper, 100 megagauss. 100 megagauss is 10 kilotesla. Okay. The magnetic field is of, the laser pulse is of femtosecond duration, but the magnetic field is of picosecond duration. So if you finish your experiment within picoseconds.
But those are measured values?
Yes, those are measured.
How you measure such a high?
Okay, so these measurements were done using Cotton-Mouton polarimetry. So what you do is it's called a pump probe experiment. Okay, so I cannot. Basically, you send a light, and the magnetic field changes the polarization of the light, and you measure the polarization, change in polarization. Okay. Faraday effect gives you the longitudinal magnetic field. The transverse field will come from the cotton wool, right?
Those electric field, they don't change the properties of plasma and then that longitudinal electric field
Yes.
which you generate. They don't change the properties of plasma itself.
I didn't
Plasma
understand.
in which you are putting the waves. The electric field which you have generated due to this.
Electric field has been generated by the electrons. Electrons rearrange themselves in such a way that the net force on them is 0. So plasma property has changed. You will have pile up of electrons in one place and deficiency of electron in another place. So this creates an electric field which accelerates ions.
But possibly the plasma should shield that electric field. Property of plasma.
No, it is shielding, it is trying to shield. So it is moving electrons. You can see from the figure here. I do not have a plot of the electron density, but okay, this one. Okay, maybe you should see the static picture. The blue light here, blue color here is the electric field, the longitudinal electric field. This experiment, if completed, I am 100% sure this will be nature work. Should be. Because right now they are waiting for the petawatt laser to come so that they can do the experiment with 10 to the 19 watts per centimeter square. So with the current laser, they could only get 10 to the 5 neutrons per steradian per joule. This is measured. This is measured. Okay, but this is only with a single Whistler wave. So you can always ask how come a single Whistler wave is generating electrostatic field. The thing is, if you have a Whistler pulse, then it can exert a ponderomotive force on the electrons and generate an electric field. Okay. Thank you. I finished before time.